All right, so these notes for trig equations we're going to split across 2 days. So we're basically combining our unit circle knowledge with our trig identity knowledge, and now we get to solve equations. So we have solved equations before, just from 0 to 2 pi, but now basically our equations might have to use identities. So we did this back in chapter 4. We're going to use some of that skill with a little bit of what we know now. Okay, there are different types of trig equations. Basically, there are like 3 types. A single trig function. So let's take a look at number 1. Number 1 just has a single trig function versus something that could be factored or something that has multiple trig terms. So we're in scenario 1. Isolate the trig term. All right, so sorry. So for this one, isolate the trig term means add 1, divide by 2. We're trying to solve sine of x equals 1 half. The directions, by the way, say solve for all values of x in the domain. So that's not just 0 to 2 pi. We might start there, but then we're going to have to add some integer values, integer multiples. All right. Isolate the trig term, done. Determine the 2 angles between 0 and 2 pi that satisfy the equation. And then once we do that, add 2 pi k. K is an integer. We've seen that before. Why do we add 2 pi k, and will that ever change? So it's always going to be 2 pi k because we are getting coterminal angles. That means that if pi over 6 is an answer, then so is 13 pi over 6, and so is 25 pi over 6. And every multiple of 2 pi, I could add or subtract circles to that pi over 6 answer and get another answer that solves the equation as well. There are infinitely many answers. So you do that for each x. And then you solve for x. So let's do that. Think about 0 to 2 pi first. So sine is positive in quadrants 1 and 2. And what angle, what's my reference angle here? My reference angle is pi over 6. That's what makes sine equal to 1 half. So our answers for x to begin with are pi over 6 and, actually I want to write it out this way, pi over 6 and 5 pi over 6, quadrant 1 and quadrant 2. And then how do I find the infinitely many answers? I just say pi over 6 plus all the coterminal angles, 2 pi k, k's. Actually, you know what? Let's put the little integer statement at the end. Pi over 6 plus 2 pi k, and then also 5 pi over 6 plus 2 pi k. And for both of those, k is an element of the integer number set. All right, so that's it. If this were 2x equals, 3x equals, I would set that equal to pi over 6 plus 2 pi k and solve from there, which we'll see. Okay, number 2. Number 2 has multiple trig terms, but they're both the same thing. See how this is sine x and this is negative sine x? It's not sine squared or tangent or something. So let's get the trig terms on the same side to isolate them. So let's add sine x over here. So if I add sine x, I get 2 sine x plus radical 2 equals 0. So now it's a single trig function. Let's isolate that trig function. So sine x is equal to negative radical 2 over 2. All right, now in this problem, sine is negative. That happens in quadrants 3 and 4. And the reference angle we should be thinking about, what makes sine equal to radical 2 over 2? That's pi over 4. So my initial answers are x equals, in quadrant 3, that's 5 pi over 4. And in quadrant 4, that's 7 pi over 4. And we want infinitely many answers, so let's add to that 2 pi k. And for both of those, k is an integer, is an element of the integer number set. All right, let's look at next one. So 3 tangent squared minus 1. Even though this is tangent squared, it's still a single trig term. So let's isolate the trig term to begin with. So tangent squared x equals 1/3. Square root both sides. Now, when you introduce a square root to an equation, when you square root both sides, it's plus or minus 1 over radical 3. Now, don't bother rationalizing that because you're trying to figure out the reference angle. So tangent is positive or negative in all 4 quadrants. So we need 1, 2, 3, and 4. So we just need to know the reference angle. What is the reference angle here? So what angle has a y of 1 and an x of radical 3? That is pi over 6. So if I want to answer in all 4 quadrants, it's going to be the first pi over 6 angle plus 2 pi k. The next one, 5 pi over 6 plus 2 pi k. 7 pi over 6 plus 2 pi k. And 11 pi over 6 plus 2 pi k. Remember, adding 2 pi k does not get you from 1 pi over 6 to the next. The difference between these is not a full circle. So that's why we have to list out all 4 of them and then say k is an integer. So all of those so far were a single trig term. What about the next one? What if we have something that's factorable? So if I have something that's looks like a trinomial, or maybe I see a GCF or something, start by making sure it's equal to 0. So check. And then factor completely. So this is going to be 2 sine x and sine x. Factors of 1 have to be 1 and 1. I need to get negative 1 in the middle, so this gives me minus 2 sine, and this gives me plus sine. So that's going to give us our negative sign in the middle. So this is the correct factoring. And then remember, when you factor something, if it's equal to 0, you set each factor equal to 0. So if 2 sine x plus 1 equals 0, then sine x equals negative 1/2. And if sine x minus 1 equals 0, then sine x equals 1. All right, so sine is negative in quadrants 3 and 4. The reference angle I should be using is pi over 6 to make sine equal to 1/2. So the answers from this section, what's the pi over 3, or what's the quadrant 3 angle of pi over 6? It's 7 pi over 6 plus 2 pi k. What is the quadrant 4 version? That is 11 pi over 6 plus 2 pi k. Kez. There's one set of answers. When is sine equal to 1? So this is not a quadrant, this is a non-quadrant. So you should be thinking about your 4 corners here, and this is at 0, 1. Sine is equal to 1 at pi over 2. 3 pi over 2 would be negative 1, so it's just pi over 2 plus 2 pi k. K is still an integer. All right, now be careful on the factoring problems. Here's a case where this looks like a nice little trinomial, except your trig terms have to match. So this is actually like scenario 3, multiple trig terms. So if we have multiple trig terms, we might need to use identities to get into one of these other types, something factorable or a single trig function. So if I want to use identities, the only thing I can swap out right now that I have an identity for is sine squared. We've been using this trick that sine squared is equal to 1 minus cosine squared. And then everything else is just going to fall into place. I'm not subbing out anything else, I mean. And then we're going to distribute the 2. So 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. 2 minus 3 is actually minus 1. Now, I don't like factoring with a negative squared term, so I'm going to move everything to the right side, or you can think of it as like multiplying both sides by negative 1, whatever, but I want it to be positive cosine squared x minus 3 cosine x. Instead of minus 1, it's going to be plus 1. And now I can factor. 2 cosine squared is 2 cosine and cosine. The only factors of 1 are 1 and 1. To get negative 3 in the middle, I need to make both of those minus, so that this becomes minus 2 cosine and this becomes minus 1 cosine. That's going to give me the negative 3 that I need. If the first factor is equal to 0, then cosine x is equal to add 1 divided by 2. If the second factor is equal to 0, then cosine x would equal 1. Cosine is positive in quadrants 1 and 4, and the reference angle that makes cosine equal to 1/2 is pi over 3. So x equals pi over 3 plus 2 pi k, and x equals 5 pi over 3, that's the quadrant 4 angle, plus 2 pi k. K is an integer. When is cosine equal to 1? That's not a quadrant, that's a non-quadrant angle. So when is the x coordinate around the circle equal to 1? That is at x equals 0 plus 2 pi k. Now you need that plus 2 pi k because that means 0, 2 pi, 4 pi, 6 pi, or 0, negative 2 pi, negative 4 pi, whatever. Now, do we need to leave the 0 in there? Not necessarily. You could just say x equals 2 pi k. If we were looking for solutions on an AP exam, I'm sure it would just say 2 pi k there. All right. What about some of these other problems? We're going to finish out, we're going to stop at inequalities. We're going to finish these last 3 examples. Okay, so sine of 2x equals negative radical 3. I'm not going to use identities unless I have to. So if I see sine of 2x, I don't want to use a double angle identity because that makes more than one trig function involved. But I'm going to isolate this trig term. And I'm still saying, okay, sine is negative in quadrants 3 and 4. The reference angle that makes sine radical 3 over 2 is pi over 3. So here's the difference in this one. It's 2x. So it's not x equals, it's 2x equals. So quadrant 3, 4 pi over 3. You need to add the plus 2 pi k here before you solve. And also 2x will equal 5 pi over 3, that's quadrant 4, plus 2 pi k. Now, when I solve for x, I've got to divide by 2. You need to divide everything by 2, including the 2 pi k. That's important. All right, so x equals 4 pi over 3 divided by 2. So 4 pi over 3 times 1/2. The 4 and the 2 reduce. So that's 2 pi over 3. Instead of plus 2 pi k, it's now plus pi k. Okay, so why is that the answer? Because you're putting that in for x, and back into the original equation, you would put it in for x and multiply that whole thing by 2 to get back here. And we know that makes sine equal to negative radical 3 over 2. Same thing on this one. 5 pi over 3 times 1/2 is going to become 5 pi over 6 plus pi k. And for both of those, k is an integer. All right. Now, I don't have a choice here about using identities because I have multiple trig functions. So if I have multiple trig functions that are different, I need to expand out. So double angle formula says this is 2 sine x cosine x minus cosine x equals 0. Using that identity got me into something I can factor. I see a GCF here that I can factor out. So factor out a cosine x. That's 2 sine x minus 1. And because this is equal to 0 and I've got it factored, I can set each part equal to 0. So cosine x equals 0 or sine x equals 1/2. When is cosine x equal to 0? So these are non-quadrant angles, and there are 2 answers here, top of the circle and bottom. So x equals pi over 2 plus 2 pi k, and x equals 3 pi over 2 plus 2 pi k. Nothing extra to solve for because the angle was just x, it wasn't 2x. So I write k as an integer. So that's that first set of answers. Okay, and then sine is equal to 1/2. That sine is positive in quadrants 1 and 2. Reference angle is pi over 6. So x equals pi over 6 plus 2 pi k, and 5 pi over 6 plus 2 pi k, and k is an integer, of course. Okay, final problem here. 4 cosine of 3x equals 2. So again, it's a single trig term. We don't want to use identities. Plus cosine of 3x, we'd have to use like a sum or difference with 2x and x. We don't want to do that. So isolate this first. Cosine of 3x equals 2 over 4, which is 1/2. Cosine is positive in quadrants 1 and 4. The reference angle that makes cosine equal to 1/2 is sorry, the reference angle that makes cosine equal to 1/2 is pi over 3. And then we say, okay, 3x needs to equal um, pi over 3. Sorry, I'm distracted over here. And 3x needs to equal 5 pi over 3. And we add 2 pi k to both of those. So then we solve for x by dividing. So x is equal to, if we divide by 3, we get pi over 9 plus 2 pi over 3 times k. And if we divide this by 3, we get 5 pi over 9 plus 2 pi over 3k. Now, what if, actually the infinite answers I think are easier than if they say, give me all the answers from 0 to 2 pi. So if they want all the answers from 0 to 2 pi, we have formulas for those. So let's use our 3x as an example. You have formulas to figure out what those are. It's just that you're going to have to do a bit of math here, right? So you would need to allow k to be 1 and 2 and 3 until you get something that's outside of the 2 pi range. So, okay, the first solution is if k is 0, we get pi over 9. That's the first angle. Now, add 2 pi over 3 to that. So really add 4 pi over 9 because you're trying to get a common denominator. So if I add 4 pi over 9 to pi over 9, I get 5 pi over 9. Oops. There we go. If I add another 4 pi over 9 to that, another 2 pi over 3k, I get 9 pi over 9. If I add another 4 pi over 9 to that, I get 13 pi over 9. What's 2 pi? It's 18 pi over 9, right? So, okay. So if we add, oh, wait a minute. Sorry, don't add 4 pi over 9. Goodness. Flawed math. Sorry. If you add 2 pi over 3, let's try my common denominator work again. If I want this to be over, let me get my pen working again. If I want to change 2 pi over 3 to something over 9, how about I do it correctly? So that'd be 6 pi over 9. There we go. All right, so if I add 6 pi over 9 to that, I get 7 pi over 9. Add 6 pi over 9 to that, I get 13 pi over 9. We haven't surpassed 2 pi yet. Add 6 pi over 9 to that, I get 19 pi over 9. Now, that's bigger than 2 pi. 2 pi is 18 pi over 9. So here's one set of solutions from 0 to 2 pi. Don't forget, you have to do this for the other one too. So if k is 0, you get 5 pi over 9. If k is 1, again, you're adding 2 pi over 3. So you're adding 6 pi over 9. So you get 11 pi over 9. Add 6 pi over 9 to that, 17 pi over 9. If I add 6 pi over 9 to that, I get 23 pi over 9, which is too big. 17 pi over 9 is just short of 2 pi. So there is a pattern here. When the angle is 3x, you should get 3 angles for each set that you found. If I did this for number 6, because the angle is 2x, I should get 2 answers from this solution and 2 answers from this solution that fit within one full circle. And if the angle is just x, from 0 to 2 pi, I should just get one set of answers from each that fits within one full circle. All right, we're going to save the rest of the notes for tomorrow. Come to office hours if you have any questions.